All right, children, so this is our lesson 5-1 video. In it, we're going to talk about operations with functions. It's a pretty straightforward concept that just involves stuff that you already super know, combining like terms and the like. And that's really all we're going to talk about in this lesson. So EQ1 is us actually doing these operations, namely, they're arithmetical operations. So addition, subtraction, multiplication, division. And then EQ2 is just going to be, how do these kind of things arise in the real world, quote unquote, right? So let's look at adding and subtracting functions. So here we've got two functions, f and g, both are functions of x, right? So that means that we can add them, even if they weren't both functions of the same variable, we could still technically add them, but it's all to do with combining like terms, right? So what are functions? So f of x, this is a fancy way of saying y, right? So y is equal to 10x plus 80, right? So some variable is dependent upon x and this function of x therein, right? So instead of just saying, some variable is dependent upon or is a function of x, we can simply say already that this function is f of x, meaning that whatever f is dependent on whatever x is. We're already, using our notation here to just say that f depends on x. Okay, so it's far more common. You're going to see it this way, expressed this way from here on. Except in differential equations, they really like to use y a lot more than they do f or g of x. But that I'm getting off topic. Anyway, so functions are, basically we get an output from some function with an input. Okay, so just a brief review. So what are arithmetical operations? Well, they're right here in EQ1, adding, subtracting, multiplying, dividing. And now we're getting into the bigger picture. So what would f plus g be equal to? In other words, what would f of x plus g of x be if we added them, right? So all we're saying here, so f of x, well, we know that that's 10x plus 80. And we're adding it to g of x. Well, we know that's 13x minus 20, right? Now, what is this equal to? Well, it's simple math, right? So do I need any of these parentheses? Well, no. There's not anything being distributed into them, save for an imaginary positive 1, right? So right now, it just comes down to combining like terms, something that we're really good at already from all the elimination and substitution we've been doing with solving systems. So 10x, 13x, they're like terms that can be combined. We can say that that's 23x in total, plus 80 minus 20, so that leaves me with plus 60. So to answer our question, what is f plus g? Well, it would be equal to 23x plus 60. And you'll see this written out in a number of ways, right? So here I wrote it very simply as literally f of x plus g of x, or you'll see f plus g of x. They both mean the same thing, okay? All right, so moving on to the next one. What about g of x plus f of x? Well, all we're going to do now is just flip this, right? But is anything really going to change? And the answer is no, nothing's going to change. So g of x plus f of x is still going to be equal to 23x plus 60. And why is that? And this is going to seem really stupid, but 2 plus 3 equals 5. And so does 3 plus 2. Okay, this is called the commutative property, right? And this only applies to addition. Okay, we can't necessarily apply it to subtraction. We can. Subtraction is the same thing as addition. It's adding a negative. But just to not be confused, right? You can really only do this if we're talking about adding, not, finding a difference. Okay. So number 5, what would f of x minus g of x be? Well, f of x, so 10x plus 80 minus g of x, 13x minus 20, right? So now we do need these parentheses, okay? I need to distribute this minus, which is an imaginary -1, into these two terms here in the grouping. So what I've really got is 10x. I'm going to drop the parentheses on the left because I don't need them. There's nothing being distributed into them. So 10x plus 80. So this here gives me negative 13x or minus 13x. And then this here gives me positive 20. Okay, because negative times a negative. You get the idea. And again, all we're doing is combining like terms. So plus 10x minus 13x. So that's negative 3x. Plus 80 plus 20, this becomes plus 100. Okay, so f of x, or f minus g of x, is equal to this guy right here, negative 3x plus 100. Okay, so now, what about g of x minus f of x? So this goes back to what I was saying, right? The commutative property, it does apply to we call it addition, but it does not apply to subtraction. Okay, so you'll see what I'm talking about here. So now we're doing it the other way around. So g of x, so 13x minus 20, so that's g of x. We're doing number 6 here. Okay, minus f of x. So that would be 10x plus 80, right? So I do have to distribute on the right. On this left term, I don't need to distribute anything, so I'm just going to say 13x minus 20 minus 10x minus 80. I distributed the minus. Okay, combine like terms, plus 13 minus 10x, that's going to be positive 3x, minus 20 minus 80, that's going to be minus 100. So this is what f minus g, sorry, not f minus g, this is what g minus f of x would be equal to, right here. Okay, and you can clearly see they're not equivalent. Okay, they're not equivalent. So here on number 7, which was commutative? Well, adding. Okay, so example 2, we've got 3 functions here, and now we're going to be multiplying and dividing. Okay, so pretty much the same idea. So what would m times n be? And another way to say this, m times n of x, or you may see it with the dot, so m times n of x, right? Either way, all 3 of these still mean the same thing. So let's see, what would m times n of x be? Well, so m of x, well, that's 6x, times n of x, that's 12x. Okay, so we multiply, 6 times 12 is 72, right? These are our constants multiplying together. X times x would be x squared. Okay, much in the same way that we say 3 squared is equal to 3 times 3, right? X squared is equal to x times x. Okay, so just a little refresher there in case you had a brain fart on where I got that from. Okay, so my answer here, my answer here would be m times n of x is equal to 72x squared. What about the other way around? Again, we see the commutative property at play here. 2 times 3 equals 6. But it's also true to say it the other way around. 3 times 2 also equals 6. Okay, so the commutative property applies to both addition and multiplication, because multiplication is the same thing as adding. It's just a shortcut for it, right? Okay, so that said, it does not apply to division. Okay, so number 2, I can go ahead and say my answer is going to be exactly the same, right? N times m of x is just going to be the exact same thing as m times n of x because of the commutative property, which means it's also going to be 72x squared. And that's because even if I do it the other way around, that would be 12x times 6x. That still gives you 72, 6 times 12, x squared, x times x. Okay, so now p times m. Okay, so p of x, x plus 1, times m of x, 6 times x, or 6x. Okay, and this might look a little bit confusing, but what I'm really saying here, if I just kind of reconfigure it, right, because of the commutative property, I can say that this is really 6x times x plus 1, and we very plainly see that all we need to do is distribute the 6x into the parentheses. So this is going to give me 6x squared, right, because 6x times x, plus 6x times 1, which obviously is just itself, 6x. Okay, so this would be equal to p times m of x. Okay, so now we're getting into division. What is m of x over n of x? And we see this a little bit in the do now. So all I'm literally going to write it as is a rational expression just like this. And you won't always see it this way. Sometimes you might see m over n like that. Or you might see m divided by n of x. Either way, it all means the same thing, just the rational expression of m of x over n of x. So to write that out, m of x over n of x. Okay, so there we literally have it. So 6x on top, that's m of x over n of x. Okay, and now we have to think, well, it's just a fraction, right? So can we reduce? Well, 6 over 12 reduces down to just 1/2, so I'm left with x over 2x. But what about x over x? If we look at it by itself, x over x, well, that's just like saying, what's 2 over 2? Well, obviously that would just be 1. So x over x, analogously, is also 1. So x over x, we're left with just 1/2. So m divided by n of x is simply 1/2. Always simplify where you can. Okay, so what about n over m? So, like I said before, the commutative property does not apply to division. Okay, so this would be the same thing as number 4 except written upside down. So n of x, which is 12x, over m of x, which is 6x. 12 over 6 is 2. X over x is 1, so our answer would simply be 2. 2 is equal to n over m of x. Okay, so what is the domain restriction? What is the domain restriction, running out of colors here, of n over p of x? So n 12x over, so that's n, over p of x, which is x plus 1. Okay, so would there be a domain restriction? Well, let me ask you this, right? And we talked about this in the do now. So could you have something 2 over 0? Well, no, that's ridiculous. You would have something infinite, right? So right here, what would give us something infinite if we chose to put it for x in our denominator? Well, if we said x equals -1, so if I said 12 times -1 over -1 plus -1, what am I going to have? Not -1, positive 1. -1 plus positive 1, right? Because I have a plus 1 here. Okay, so that would give me -12 over 0, which is, we can't have that, right? We want to deal with finite values. Okay, so we could say 12 over x is equal to, 12x over x plus 1 is equal to n over p of x, right? But we would also have to say that x cannot be equal to -1 for precisely this reason. We'll get something infinite and crazy. Can't have that. Okay, so which operation was commutative? Well, obviously, multiplication was commutative. Okay, so now we've got some more problems to practice with. Okay, so f plus g. So I'll use blue here. So f plus g, so that would be 3x plus 2 plus g, so plus 2x minus 1, right? And we see right off the bat, we don't really need the parentheses because we're not distributing anything. But always, always, always play it safe. Write it out as is, okay? So just combine like terms. So 3x, 2x, that gives me 5x, plus 2 minus 1, that gives me plus 1. So f plus g is equal to 5x plus 1. Okay? Now I have h plus f. Okay, so that's going to be h x squared minus 2x plus 8 plus f 3x plus 2. And again, I didn't need the parentheses, but I'm just trying to make a point here. It's always good to use them because when you start messing around with a whole bunch of sign changes and things, right, stuff can get confusing. So x squared, that's not going to combine with anything. We're just going to go ahead and write that guy again. Minus 2x plus 3x, that leaves me with plus x, plus 8 plus 2 leaves me with plus 10. So h plus f is equal to x squared plus x plus 10. All right, so now we have g minus f. So g, 2x minus 1, minus f, 3x plus 2. Okay? I am going to need the parentheses on the right, but I don't need them on the left. On the right, I'm going to have to distribute this minus. All right, so that's going to give me 2x minus 1 minus 3x minus 2. Combine like terms. 2x minus 3x negative x minus 1 minus 2, that gives me minus 3. So g minus f is equal to negative x minus 3, f over g, right? So f divided by g. So that would be 3x plus 2 over g, which is 2x minus 1. Okay, so I can't simplify anything like I could back here, where I had the real cute, fractions that I could reduce by, right? Over here on number 4, I can't do that. I don't have any common factor between 3x plus 2 and 2x minus 1. So be careful not to get confused on that. We cannot cancel the 2x's because not all 4 terms, right? Not all 4 terms have an x in common. Okay, and we'll talk about that more later on. Okay, you're not going to see anything that crazy. But let's answer this piece right here. Are there domain restrictions? So is there some value of x that I can plug in here that would give me a 0 in the denominator and ultimately make me make me have a number that is infinite, okay? So maybe you can't tell off the top of your head what it is, right? The simple way to do it is take the denominator, so the 2x minus 1, and set it equal to 0. What we're saying is, what value of x would make this be equal to 0? If we set it equal to 0, we'll be solving for the literal x that will make this denominator be equal to 0. Okay? So I'm going to solve this. So 2x equals 1. Divide by 2 on both sides. X equals 1/2. And let's see if that's true or not. Right? So if I actually plug that in, so 3 times x plus 2 over 2 times x minus 1. Well, 3 times 1/2, that's just 3 over 2 plus 2, over 2 times 1/2, well, that's 1 minus 1. Very plainly, 1 minus 1 is going to make us divide by 0. So we would have, 3.5 over 0 or something infinite. And we do not want that. No, 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 no. Okay, so our domain restriction will simply be that x cannot be 1/2. So we would just put a comma. So f over g of x is simply this right here, 3x plus 2 over 2x minus 1. But x must from our domain, we must exclude 1/2. We must say that x cannot be 1/2, or that it is excluded from our domain. Okay, so I'm going to cycle some colors now. So f minus g, so 3x plus 2, oops, and then minus g, so minus 2x minus 1. Okay, so don't need the parentheses on the left, but I do need them on the right so that I can distribute the minus. So negative 2x, that's what I got there, and positive 1, what I got there. Combine like terms, 3x minus 2x, just x, plus 2 plus 1 plus 3. So x plus 3 is equal to f minus g. And now we're going to do h minus g. Okay, so h, x squared minus 2x plus 8, minus g, 2x minus 1. Okay, don't need the parentheses on the left, but I do need them on the right. So negative 2x plus 1, just like before. Right, now combine like terms, so the x squared combines with nothing, so that's just going to stay x squared, minus 2x minus 2x minus 4x, that's what that becomes, plus 8 plus 1, that gives me plus 9. So x squared minus 4x plus 9 is equal to h minus g. Okay, and now we're looking at h over g. Right, so h over g, so that would be x squared minus 2x plus 8, that's h, over g, which is 2x minus 1. Right, so 2x minus 1, well, we already did the math for this earlier. We already know 1/2 is going to make that denominator, if it's 2x minus 1, 1/2 is going to make that denominator be 0. So we would say this is our function, h of x over g of x is equal to x squared minus 2x plus 8 over 2x minus 1. And we would say that we want the domain restriction such that x does not equal 1/2. Okay, so now a real world quote unquote example. So we got Jumpy Jeffrey and Paranoid Pete. They're still messing with that jetpack that Elon Musk designed. So originally the jetpack accelerates Jeffrey at a rate of 32 miles per second squared, right? Which means 32 miles per second per second. So every second he's going 32 miles an hour faster. But now it's got a turbo booster attached to it. And the turbo booster, in theory, by itself, right, if he was only wearing the turbo booster, it would accelerate Jeffrey at a rate of 16 miles per second squared on its own. Okay? So, like me, Pete is more the math buff than he is the physics nerd. So he's not sure if the turbo booster will add to the jetpack's rate of acceleration, like literally just add to it, and it becomes 48 miles per second squared, or if the relationship between them would be multiplicative, meaning you would multiply 32 times 16. So common sense kind of tells me, because I do know about vectors, this is more of a question for Mrs. Delino, but the point is we can actually apply what we were just doing here, right? So if we derive a velocity function, j of t, for the jetpack's original acceleration, well, the jetpack's acceleration is simply, or the velocity is simply equal to 32 miles per second squared, right? So every second, he's going 32 miles an hour faster. Okay, so now for the booster, well, we already know the booster is giving us a velocity increasing at a rate of acceleration of 16 miles per hour per second squared, right? And if we continue, so now we're here, number 3. So calculate j plus b of t, right? So j plus b of t, well, that's real simple. So that would just become 48t. All I did was add 32t plus 16t, that's j of t plus b of t, right? And so this is where it could get potentially crazy. So calculate j times b of t. And I'm going to need a calculator for that because I don't know what that would be. So 32 times 16, so that would be 512 miles per hour per second squared, right? So, or I should just say miles per hour per second, right? So that is pretty crazy. Now, do you think the booster will literally add to the jetpack's original acceleration, or the boost will be multiplicative? Well, I can tell you this, I'm pretty sure it's not multiplicative. Now, is it that simple to just add them? Well, if we're talking about vector addition, right, it would be that simple to just add them because they're both force vectors going in precisely the same direction. So I think it would be that simple to just add them. Again, not a physicist, more of a math guy, but I don't know. Feel free to research that on your own. So that does it for this video. Let me know if you have any questions or concerns either via email or come and see me during tutoring. Otherwise, that's the end. Goodbye.